Welcome to the course on an introduction to information theory. In today's lecture, we are going to talk about how to compute channel capacity of some very simple channel. If you recall, in the introduction, we talked about what is channel capacity, and Shannon, in his celebrated noisy channel coding theorem, has mentioned that as long as we transmit at rate below capacity, we can achieve reliable communication. Now we are going to formally state Shannon noisy channel coding theorem and its prove it and prove its converse in the next lecture. In today's lecture, we will be dealing with some very simple channels. We are looking at discrete memoryless channel, and we'll try to compute capacity of those simple channels. So we'll start off with a description of a discrete memoryless channel, and then we'll describe two types of channel. One is called uniformly dispersive channel, another is called uniformly focusing channel. And channels which satisfy both of these properties are known as strongly symmetric channel, and we'll compute the capacity of a strongly symmetric channel, and subsequently we will show that there is a class of channels which can be decomposed into strongly symmetric channels, and that's basically known as symmetric channel, and we will compute the capacity of symmetric channels. So this is a plan for this lecture. So a discrete memoryless channel is specified by these quantities. One is input alphabet, which we are denoting by A, output alphabet B, and the conditional probability distribution over B for each x. So we need to describe our input, we need to describe our output, and we need to describe the conditional distribution of y given x for a discrete memoryless channel. Now as you can see, for a discrete memoryless channel, probability of yn given past inputs, which are given by x1, x2, xn minus 1, and the current input xn, and the past outputs y1, y2, yn minus 1. Because it is a memoryless channel, it does not depend on past values. So the probability of yn given x1, xn minus 1, x of n, and y1, yn minus 1, it only depends on the present input. Because it is memoryless, it does not depend on past values of xi's, it does not depend on past values of y's. It only depends on the current value of x. So for a memoryless channel, probability of yn given past values of y's or past values of x, it only depends on the current value of x. So probability of yn given x1, x2, xn, y1 to yn minus 1, it only depends on yn given x of n. Now we see a discrete memoryless channel without feedback as follows. So probability of x1, x2, probability of xn given x1, x2, xn minus 1 and y1 to yn minus 1, it only depends on probability of xn given x1 to xn minus 1. So it does not depend on the past values of the output. So this is our discrete memoryless channel without feedback. So for a discrete memoryless channel without feedback, we can write probability of y1, y2, yn given x1, x2, xn as this product of these probabilities of yi given xi. So this we can prove in this particular fashion. We write the joint probability of x1, x2, xn, y1, y2, yn. So this can be written in this particular fashion. So product of I going from 1 to n, probability of xi given x1, x2, xi minus 1, y1, y2, yi minus 1, probability of yi given x1, x2, xi, y1, y2, yi minus 1. Now, because it is a memoryless channel, this term is equal to this. So probability of yi given x1, x2, xi and y1, y2, yi minus 1, it only depends on present value of the input. So this term can be written in this particular fashion, and since we are talking about discrete memoryless channel without feedback, so this term can be written. So probability of xi given x1, x2, xi minus 1 and y1, y2, yi minus 1, it does not depend on this, it only depends on these values. So I can then write it in this particular form. So then I can write this in this particular fashion. And what is this term? This term is nothing but probability of x1, x2, xn multiplied by this term. Now if I divide both sides by this, on the left hand side I will get this, on the right hand side I will get this. So hence this proves that if I have a discrete memoryless channel without feedback, probability of y1, y2, yn given x1, x2, xn is given by this expression. Probability of yi given xi and product of that, all of these. Now, we define channel capacity of a discrete memoryless channel as the maximum average mutual information that can be obtained over choice of P of x. So, capacity is defined as maximum mutual information between the input and output of a channel, and this maximization is taken over all possible input distribution. Now, mutual information we can also write from the definition of mutual information, we can write it as uncertainty in y minus uncertainty in y given x. So equivalently we can write the expression of capacity as maximizing the difference between h of y minus h of y given x, maximizing over all possible input distribution P of x. Now let us consider some very simple channel. So first channel that we will consider is what is known as uniformly dispersive channel. So we are considering a discrete memoryless channel which has k inputs and j outputs. For example, in this particular case, k is equal to 2 and j is equal to 3. Now we say a discrete memoryless channel is uniformly dispersive if the probabilities of the j transitions leaving an input when put in descending order has the same values for all k inputs. So what does it mean? So we look at each of these inputs, we look at each of these k inputs and we write the transition probabilities leaving that particular input. So for example, take this input 0. So what are the three transition probabilities? This is half, because this transition probability is half, this transition probability is half, and this transition probability is 0. So if I arrange this transition probability in the descending order, this will be my order. Now look at this input. This is 0, this transition probability is half, this transition probability is half. Now, if I arrange this in descending order, this would be half, half and 0. Now, what does the definition say for a uniformly dispersive channel? It says that a discrete memoryless channel is uniformly dispersive if the probabilities of the J transitions leaving an input when put in descending order has the same value for all the K inputs. Now, when I put the J transitions corresponding to input 0 in descending order, this is what I got, half, half, 0. Now, when I did the same thing for input 1, I got half, half and 0. Now, note this is same. So, when I arrange these transitions probability in descending order, it is same whether I consider 0 input or 1 input, and that is what my definition says. So, this is an example of uniformly dispersive channel. Now, for a uniformly dispersive channel, independent of the choice of input distribution, we can write the uncertainty in y given x as summation of minus pj log pj, where these pj's are transition probabilities leaving each input letter. So, let us prove this property. So, from the definition of conditional entropy of y given a particular instance of x ak, this can be written as minus summation over all possible transitions pj log pj. Now, we know that because these transitions P1, P2, P3, Pj, when they are arranged in the descending order, it is same no matter what input you consider. So, from the definition of conditional entropy of y given x, we can write this as this. Now, note this term which is given by this expression, this is same for all inputs for a uniformly dispersive channel. So, you take this out, then you are left with summation of PAK sum over all k's. So, that summation is 1. So, then we have proved that uncertainty in y given x is given by uncertainty of y given x is some ak, and this is nothing but given by this. So, we have proved that no matter what is the choice of input distribution, the uncertainty in y given x for a uniformly dispersive channel is given by this expression. Next, so then we can write down the expression for capacity for a uniformly dispersive channel. Now, what was capacity? So, this was maximizing over all input distribution h of y minus h of y given x. Now, this quantity is, no matter what's the choice of p of x, this quantity is fixed for a uniformly dispersive channel. So, minus of this is essentially given by this expression. So, in other words, if you want to find out the capacity of a uniformly dispersive channel, this is given by maximizing h of y over all input distribution p of x plus this quantity. And we know, and y is a discrete random variable, it is maximized, the entropy is maximized when it is uniform. So capacity will be maximized for the input distribution P of x, which will induce a uniform distribution on y. So this follows straight away. We just proved that uncertainty in y given x is given by this expression. Now if we plug this value here in the expression for capacity, we get our desired expression. So this is the expression for capacity for a uniformly dispersive channel. Now let us now talk about another type of channel which is known as uniformly focusing channel. So what is a uniformly focusing channel? So let us consider a discrete memoryless channel which has k inputs and j outputs. So in this particular example, k is 3 because I have 3 inputs, this one and this one. Okay, you can call it 0, 1, 2 or whatever you want to call it. And there are 4 outputs. J is 4, B1, B2, B3, B4. Now we say a discrete memoryless channel is uniformly focusing if the probabilities of k transitions to an output letter when put in decreasing order has the same value for all j outputs. So what we need to do is we need to look at the output letters. We look at B1, B2, B3 and B4 and look at the probabilities of k transitions to this output letter. So let's look at B1. The transition from here, this has probability half. B1 transition from this node 2 is 0 and transition from this has probability 1 by 4. So this is what this particular output. Look at this particular output. Transition from this particular input 0 has probability 1 by 4. Transition from here has probability half and transition from here, this is 0. There is no transition. Similarly B3, there is no transition from this input 0. From this input transition probability is half and from this input the transition probability is 1 by 4. And for this particular output, transition probability from 0 is this one, 1 by 4. Transition probability from this particular input is 0 and transition probability from this particular input is half. So if I arrange all of them in the descending order, for whether I consider this output, this output, this output or this output, I'll get this. So note that, so probabilities of all these k transitions to any output letter when put in decreasing order, if they have the same values for all j output, then it is a uniformly focusing channel. And in this case you can see, if I put this in descending order I get this, if I put this in descending order I get this, if I put this in descending order I get these probabilities. Similarly, if I put this in descending order I get this. So no matter what my output is, whether it is B1, B2, B3 or B4, I get the same probability order, half, 1 by 4, 0. So this is an example of a uniformly focusing channel. Now let's go back and look at this example that we did. Is this a uniformly focusing channel? Let's look at this. So if you look at B1, the transitions from here is half. From this particular node, there is no transition. What about this node? The transition probabilities are half and half. And transition for this particular node, the transition probabilities are 0 and half. So you can see this is not an example of uniformly focusing channel. Why? Because when I arrange the transition probabilities in the descending order, for these particular output B1 and B3, it is half and 0, whereas for this particular output it is half and half. So this is a uniformly dispersive channel, but it is not a uniformly focusing channel. Similarly, look at this example. Is this a uniformly dispersive channel? So for the uniformly dispersive channel, what we need to look at? We need to look at the transition probabilities leaving that particular input. For this particular input 0, these transition probabilities are half, 1 by 4, 1 by 4. For this, these transition probabilities are, so just a minute, this is half, this is 1 by 4, this guy is 0, and this is 1 by 4. For this is 0, 0, this is half, and this is 0. So clearly, if I arrange these probability in the descending order, if I arrange this probability in descending order, they are not same. So this is an example of a uniformly focusing channel, but it is not a uniformly dispersive channel. So I hope the difference between a uniformly focusing channel and a uniformly dispersive channel is clear. Now, what can we say about a uniformly focusing channel? For a k input j output uniformly focusing channel, uniform input probability distribution will result in uniform output distribution. So let's prove this. And also, maximum value of h of y is given by log of j, where j is the number of possible output values. So p of y can be written in this particular way, right? Now, if we consider uniform input distribution, since I have k inputs, so p of x will be 1 by k. So if I plug this value of p of x here, then p of y becomes this. Now what is this term? These are the transitions terminating at output y coming from all possible inputs. Now for a uniformly focusing channel, this term is same no matter what is the value of y. In this example, if you see, whether my output is B1 or B2 or B3 or B4, summation of probability of y given x is same whether I consider y to be B1, B2, B3 or B4. So for a uniformly focusing channel, this term is a constant. So if this is a constant, then probability of y is a constant. So that's a uniform distribution. So for a uniformly focusing channel, if your input is uniform, then it will induce a uniform output distribution. And since maximum value of h of y is, then we know that h of y lies between 0 and log of j. So an input distribution will result in output distribution which is also uniform, and maximum value of h of y for a uniformly focusing channel is given by this. Now what about channels? So if you noticed, for a uniformly focusing channel we were able to get maximum value of this, and for a uniformly dispersive channel we were able to get the expression for h of y given x. So, what if a channel is both uniformly dispersive and uniformly focusing? Then we have the exact expression for this capacity, and that is what we are showing. So, a channel which is both uniformly dispersive and uniformly focusing is known as strongly symmetric channel. So, a discrete memoryless channel which is both uniformly dispersive and uniformly focusing is known as strongly symmetric channel. So, I have given an example, let us just check. So, for it to be uniformly dispersive, we will have to look at transitions leaving an input. So, what are these transitions? Probability, this is 1 minus epsilon and epsilon. Similarly, here the transition probabilities are 1 minus epsilon and epsilon. Epsilon is typically a smaller number. If I arrange them in descending order, no matter whether I consider input 0 or 1, these probabilities are, the order of these probabilities are same. So, this is an example of a uniformly dispersive channel. Now, let us look at the output 0 and 1. So, what are the transition probabilities of bits terminating of the transitions from the input? This is 1 minus epsilon, this is epsilon. Similarly, here is 1 minus epsilon and epsilon. So, this is an example. So, these probabilities again when arranged in descending order, they are same no matter what is my output. So, this is an example of a uniformly focusing channel. So, this is a uniformly dispersive channel as well as uniformly focusing channel. So, this is a strongly symmetric channel. In fact, this channel is known as what we call binary symmetric channel. So, binary channel, inputs are binary, output are binary, and it is symmetric. This is a binary symmetric channel, and it is typically used to model. If we use additive white Gaussian noise channel followed by hard demodulation, we can model this channel, that channel by a binary symmetric channel. So, then since this channel is strongly symmetric, can we find out its capacity? The answer is yes. What was the capacity of dispersive channel? Capacity of dispersive channel is this, right? Maximizing h of y over p of x. Now, for a uniformly focusing channel, we know what this quantity is, and for a uniformly dispersive channel, we know what this quantity is, right? Since a strongly symmetric channel is both uniformly focusing and uniformly dispersive, we know exactly what is the expression for channel capacity for a strongly symmetric channel. So, this will be log of j plus summation of pj log pj. So, the expression for capacity for the strongly symmetric channel is given by this expression. All right. So, if you have a strongly symmetric channel with k inputs and j outputs, then channel capacity is given by this expression. We know from the uniformly focusing property that the distribution that maximizes h of y is uniform distribution, and the maximum value of h of y corresponding to this uniform distribution is given by log of j, where j is the number of possible outputs. And for a uniformly dispersive channel, we know irrespective of the input distribution, h of y given x is given by minus of this quantity. So, we know exactly the expression for capacity of a strongly symmetric channel. So, then can you tell me what is the expression for capacity of this binary symmetric channel. So here J is 2, so log of 2 is 1, so the capacity is 1 minus, and these probabilities are 1 minus epsilon epsilon, so this can be written as binary entropy function of epsilon. So this is the expression for capacity for a binary symmetric channel. And you can see, so for example, if epsilon is half, that means there's 50% probability of making a mistake. So you can see in that case capacity is 0, which is intuitively correct because it's completely randomly flipping the bits to zeros and 1 with equal probability. Okay. And another point to be noted is the input distribution that causes, basically input distribution that achieves capacity is uniform distribution, because we know for a uniformly dispersive channel, irrespective of what my input distribution is, h of y given x is given by minus of this quantity, and this quantity h of y is maximized for uniform input distribution. So the distribution that achieves capacity for a strongly symmetric channel is uniform input distribution. So if P of x is 1 by k for all x, then that will achieve capacity for a strongly symmetric channel. Now we are going to talk about a class of channels which can be decomposed into strongly symmetric channel. So this we call as symmetric channel. So a discrete memoryless channel is said to be symmetric if it can be decomposed into L strongly symmetric channel with selection probabilities given by Q1, Q2, Q3, QL. So look at this particular channel. Look at this particular channel. Is this a strongly symmetric channel? This is not a uniformly focusing channel. You can see if I consider this output, my probabilities are 1 minus delta, 0, 0, and if I consider this particular output, my probabilities are delta, delta, and if I consider this output, my probabilities, transition probabilities are 0 and 1 minus delta. So you can see if I consider this particular state, which I call erased state, my probabilities are different from if I consider this particular output. So this is not a uniformly focusing channel, even though this is a uniformly dispersive channel, because the probabilities, if you look from the input size, these transition probabilities are 1 minus delta, and this is 1 minus delta, delta. This is a uniformly dispersive channel, but it is not a uniformly focusing channel. So this is not a strongly symmetric channel, but it can be decomposed into a strongly symmetric channel. Now look here. So if you noticed, these inputs 0 and 1, they have the same focusing, because these probabilities, when arranged in the decreasing order probability, is 1 minus delta 0, this is 1 minus delta 0. So I can decompose this into two channels. One is this channel corresponding to the output 0 and 1, and other one is corresponding to this particular input. So I am decomposing this channel into two channels. One is this particular channel and other is this particular channel. Okay, and with this probability Q1, I am going to select this channel, let us call this channel 1, and with probability Q2, I am going to select this channel 2. Now note that these two channels are exactly equivalent. Why? So look at transition probability from this input to this output. This is 1 minus delta. This is 1 minus delta into 1. Okay. Now look at transition probability from 0 to this particular output, that is delta. So this is delta into 1. Similarly, when you consider this particular input, the transition probability to this particular output is delta. So from 1 you can go to this state, this delta into 1, this is exactly same, and 1 to 1, so 1 to 1, this is 1 minus delta into 1. So these two channels are exactly equivalent. Another point we noted, this channel 1 and channel 2 are strongly symmetric channel. You can verify this is uniformly dispersive because the probability in descending order is 1 and 0 for whether I consider this input or this input. This is also uniformly focusing. If I consider the output 0 or 1, again the probability arranged in decreasing order will be 1 and 0. So channel 1 is strongly symmetric. Similarly, channel 2, this is obviously uniformly focusing because there is only one output, and this is uniformly dispersive also because the probabilities are 1 and 0 when arranged in decreasing order. So channel 1 and channel 2 individually are strongly symmetric channel, and you can think of it as we are selecting channel 1 with probability 1 minus delta and channel 2 with probability delta. Now why are we doing this? Why are we trying to decompose this symmetric channel into strongly symmetric channel? That is because we know exactly the capacity of a strongly symmetric channel. So if we can write a symmetric channel in terms of strongly symmetric channel, perhaps we can get the capacity of a symmetric channel as well, and that's where we are headed. So let us go over an algorithm to partition or to see whether we can partition any channel into strongly symmetric channel. So what are the conditions that needs to be satisfied for us to be able to partition a channel into strongly symmetric channel? So we are describing the algorithm to determine whether a discrete memoryless channel is symmetric channel or not, and a symmetric channel can be partitioned into strongly symmetric channel. So the first step is partition the output letters into subset B1, B2, BL such that two output letters are in the same subset if and only if they have the same focusing. Now what do I mean by same focusing? So if you look at those output letters, and if you look at the transitions from the input to those letters, when they are arranged in the decreasing order, it should be same. For example, if you look at this particular example, you see that 0 and 1, these outputs have the same focusing because the probabilities are 1 minus delta and 0, right? And that's why we club them together. So what we are saying is you partition your output letters into subsets B1, B2, BL such that two output letters are in the same subset if and only if they have the same focusing. Now next thing we need to do is we need to check if all input letters have the same dispersion into the subset Bi of output letters. So we need to check. So once we partition the output into L sets where within each set they have the same focusing. Now we need to see whether all the inputs have same dispersion into that subset. And if that is the case, then we set Qi to be equal to sum of probabilities of these transition probability into that particular set. So for example, if you go back and see this example, you see here we are reaching here with probability 1 minus delta, 1 minus delta, and that's, so the dispersion is common. So whether we are from 0 to 1, we are selecting this channel with probability 1 minus delta, whereas this particular channel we are selecting with probability delta. So if all input letters have the same dispersion into that particular subset of output letters, then we should be able to partition our channel into strongly symmetric channel, and we are going to select each of these channels with probability Qi, which is equal to sum of probabilities from the input to that particular subset Bi. And once we know these selection probabilities Qi's, then rest this probabilities we can easily find out, because we know the transition probability, for example, from this input to this output should be this into this, which is this quantity. So we can find out this transition probability, this transition probability, this transition probability. So we can find out all these transition probability by mapping the transitions from each input of this channel to this channel. And this we continue until we are able to do it for all output letters. Okay. So if I equal to L, we'll stop and we'll say the channel is symmetric with selection probabilities given by Q1, Q2, Q3, QL. Okay. And if I is not L, we'll continue until we partition all the output letters into these subsets. So this is a block diagram of how things will look like. So you can think of, I have a general discrete memoryless channel created by L discrete memoryless channel where with selection probabilities of Q1, Q2, Q3. So I have my input X, and you can think of I have L such discrete memoryless channel. I am choosing each of these channels with probability Q1, Q2, Q3, QL. So the output you can think of is I am choosing either this channel, this channel, this channel, and this is my selection probability. Okay. So X is my input here, Y is the output of discrete memoryless channel. Okay, and Z is deciding which channel is being chosen. So we are considering a general discrete memoryless channel which is created by these L discrete memoryless channel with selection probabilities given by Q1, Q2, Q3, QL. And we make these following assumptions. So all of these L discrete memoryless channel, they take as input same alphabet. So input alphabet for channel 1, channel 2, channel 3, channel L, they are all same. Second assumption, all discrete memoryless channels have disjoint output alphabets. So there is, when we partition them into L discrete memoryless channel, the output letters are disjoint. So if there is some output letter appearing in one particular set, it would not appear in any other set. So the intersection of Bi and Bj is 0, and of course the union of all these L disjoint sets should be my overall output letters. And the selection is, which is denoted by this random variable z, this is independent of x, and the selection probability is given by qi. Now the claim I am making it is mutual information between the input x and output y can be written in terms of mutual information of these individual channels, and this is the expression relating the mutual information between the input of this channel and the output of channel. So from this expression, basically, as you can see, we can write the mutual information between input x and output y as mutual information between input x and output of these individual L channels multiplied by their selection probability and sum over all such L channels. So we are now going to prove this result. So joint entropy of y and z using chain rule can be written like this: uncertainty in y plus uncertainty in z given y. Now if I tell you what my y is, now what is y? If you go back to the diagram here, y is basically either v1, y1, y2, y3, yl depending upon which channel is selected. So if I tell you what my y is, you know precisely what channel has been selected. So z is known. So there is no uncertainty in z given y. So this quantity is 0, because if you tell me what y is, I know, because my output symbols, letters have been partitioned into disjoint sets. So if you tell me what y is, I know exactly which channel has been selected. So there is no uncertainty in z given y. Hence this can be written as uncertainty in y. Now this is same as uncertainty in z plus uncertainty in y given z. Again I am applying chain rule in a different way. So from this 2 I can write h of y is equal to h of yz. This is from here I get, and this is same as this quantity. Okay. Now let us expand this particular term. So I can write this as h of z plus uncertainty in y given z is I multiplied by probability of z. So this is from the definition of conditional entropy. Now this term is given by qi, and this uncertainty. So given that I have selected ith channel, I know the output is yi. So I can write uncertainty in y given z is I as uncertainty in yi. So then I can write this expression as h of z plus summation of h of yi into qi and sum over all L such channels. Similarly, I can write uncertainty in yz given x as, using chain rule, uncertainty in y given x plus uncertainty in z given x and y, and as I said, given y there is no uncertainty in z, so this term is 0. So this can be written as uncertainty in y given x. Now I can apply chain rule again in a different way, and I can write this expression as uncertainty in z given x plus uncertainty in y given xz. Now x and z independent, so knowing x does not give me any information about z. So, this will be h of z plus h of y given xz. Next. So, from the previous expression, then I can write h of y given x as h of z plus h of y given xz. Now, I can expand this. So, I can write this in this particular fashion. So, this is uncertainty in y given x and given z is I multiplied by probability of z I. Now, if I tell you what z is, so you know exactly what channel is. So, this can be written as uncertainty in yi given x multiplied by qi. So, I have gotten an expression of this which is given by this expression, and earlier I got the expression of h of y which was given by this expression, right. So, mutual information is maximizing h of y minus h of y given x and maximizing over all input distribution. So, if I subtract h of y given x from this, h of z is common in both of them, so that gets cancelled out. What is left is this particular term. Now, what is this? H of yi minus h of yi given x. This is mutual information between x and yi. So, then I have proved that when I decompose my channel into these L discrete memoryless channel following the assumptions which I made earlier, I can write the mutual information between the input and output in terms of mutual information of the individual discrete memoryless channel. Alright, and we are going to exploit this to get the capacity of a symmetric channel. So, if we are able to decompose our symmetric channel into strongly symmetric channel, and since it is the same input which goes to all of these strongly symmetric channel, and we know that it is the uniform input distribution that maximizes, that achieves capacity. So, we should be able to get the expression for capacity of a symmetric channel if we are able to decompose it into, that is, after decomposing it into strongly symmetric channel. So, for a symmetric discrete memoryless channel, the capacity is given by this expression, which is product of capacity of these individual discrete memoryless channel multiplied by their selection probability and sum over all L such discrete memoryless channel. And it is the uniform input distribution that will achieve capacity. The proof is very straightforward. Once we have established that the mutual information between x and y can be written as summation of mutual information of these individual discrete memoryless channel multiplied by their selection probability. Now, capacity, as you know, can be given by mutual information between x and y and maximizing over all input distribution. Now, this is less than equal to, so I need to find basically Px which will maximize this. So, I write it less than equal to this. Now, remember, in case of strongly symmetric channel, it is the uniform distribution, input distribution that achieves capacity. And since I have the same input going to all of these L channels, So the input distribution is same. So the distribution that achieves capacity for ith channel, the same distribution achieves capacity for, let us say, jth channel. So that is why for a strongly symmetric channel, I can write capacity to be equal to product of capacity of the individual discrete memoryless channel multiplied by the probability of selecting that particular channel. So again I repeat, the input distribution that maximizes this for an ith channel is same whether I consider ith channel or jth channel, because it is the uniform input distribution that will achieve capacity. And since my input, if you go back to the diagram that I showed you, it is the same input which is going to, it is the same input x, it is going here, it is going here, it is going to all these discrete memoryless channel, the same input is going, and this, and since uniform distribution will achieve capacity for each of these individual channel and it is the same input, so it is the same input that will achieve capacity for this channel. So hence we have proved that capacity of a strongly symmetric channel is given by this expression. So the above expression, as I said, is satisfied with equality if and only if there exists an input distribution that simultaneously maximizes the mutual information of each of these individual channels, and we know it is the uniform distribution that will maximize this. Why? Because each of these individual discrete memoryless channel are strongly symmetric channel. Okay, so this is the uniform input distribution that will simultaneously maximizes the mutual information of each of these discrete memoryless channels. Hence, the capacity is given by summation of product of the selection probability multiplied by the probability of the individual capacity and sum over all such L discrete memoryless channel. So we will illustrate how we can decompose a symmetric channel into strongly symmetric channel, and then we will use the expression of strongly symmetric channel to compute the capacity of a symmetric channel. So take an example of a binary erasure channel. So in binary erasure channel you have two inputs 0 and 1, and you have three outputs 0, 1 and another output state which is erased state. With probability 1 minus epsilon you receive the bits correctly, and with probability epsilon you receive the bits incorrectly. Now packet data networks can be modeled by this very simple binary erasure model. You either receive the packets correctly, or if you do not receive the packet correctly, then you want to discard them. Now this binary erasure channel can be, as you can see here, if we look at the focusing of this particular input 0 and 1, they are same, and focusing of this delta is same. So first thing that we will do is we will decompose it in such a way that this particular output symbol and this particular output symbol, they belong to the same channel, like here, because they have the same focusing. You can check, this is 1 minus epsilon 0 and this is 1 minus epsilon 0, and this has a different focusing which is epsilon epsilon. So this will be a different channel. Okay, so this is my one strongly symmetric channel, channel 1, and this is my channel 2. Now what is this selection probability? This is, so from the inputs 0 and 1 I reach this set consisting of output symbols 0 and 1 with probability 1 minus epsilon. So, okay, let's make it delta because I am in the text I am following 1 minus delta. So, let's just change this notation to 1 minus delta. It's the same thing, just changing notation because I just noticed that I using this notation delta. So, I am just changing the notation. This I am writing as 1 minus delta and this as delta. So, then I can select this channel. You can see I can select this channel with probability 1 minus delta. So, this selection probability is 1 minus delta, this selection probability is 1 minus delta. If you recall and go back to the, yes. So, the first step is we are partitioning them into subset B1, B2, BL such that no two letters are in the same subset, such that two output letters are in the same subset if they have the same focusing. So, in our example 0 and 1 output letters, they have the same focusing and delta has a different focusing. So, that is kept in a different subset. So, B1 consists of output symbols 0 and 1 and B2 consists of delta. The next is check if all inputs have the same dispersion. Now, how do you check the same dispersion? From the particular output symbol, you see the probability of the transitions from the input side. Now, if you look here in this particular example, if you look at this particular example, you reach 0 from 0 with probability 1 minus delta. Similarly, you reach 1 from 1 with probability 1 minus delta, and from 1 you cannot reach 0 and from 0 you cannot reach 1. So, they have the same focusing and that is given by 1 minus delta. So, the selection probability here in this case is given by 1 minus delta. Now, if you consider the second channel, here the second channel is similarly selected with probability delta. Again, let's redraw the diagram for binary erasure channel. One minus delta, 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 1 minus delta. Now, look at how you are selecting this channel which consists of this output symbol delta. From input 1, this is probability is delta. From input 0, this probability is again delta. So, this particular channel is selected with same probability. So, whether you consider this input or this input, both have the same dispersion. And similarly, for this particular channel which consists of output symbols 0 and 1, you can see I can reach 0 with probability 1 minus delta, and from here 0 probability. Similarly, I can reach 1 with 0 probability here and 1 minus delta. So, they have the same dispersion. That means I can find out what is selection probability. So, I will select this channel consisting of 0 and 1 with probability 1 minus delta, and I will select this channel which has this erased state with probability delta. Now, what I need to do is I need to look at this probability from input to the output. In this case, this is 1 minus delta. Now, if you look here, so this probability should be 1 minus delta. I already know my selection probability is 1 minus delta. So, then this probability should be 1. Similarly, from 0 to delta, this is probability, this erased state, this probability is delta. So, 0 to this erased state, this is probability delta. So, this has to be 1, so that the overall probability is delta. And likewise, I can calculate from 1 to the erased state, again this probability is delta. So, this delta into this should be delta. So, this probability is 1. And similarly, from 1 to this probability is 1 minus delta. So, since the selection probability is 1 minus delta, this has to be probability 1. Okay. So, now my selection probability to first set of channels Q1 is 1 minus delta, and selection probability for the second set of channel is delta. Now, what is the capacity of this channel? This is a strongly symmetric channel, and this is 1 minus this capacity of this channel is 1. We can easily see this capacity is 1, and what is the capacity of this particular channel? This capacity of this particular channel is 0. We already know the expression for capacity of strongly symmetric channel, so just plug in the value. J in this case is 2, so log of 2 is 1, and the transition probabilities are 1 and 0. So, the contribution due to h of y given x will be 0. So, capacity of this will be 1, and similarly capacity here j is 1. So, log of 1 is 0, and this probabilities are 1. So, overall capacity of this particular strongly symmetric channel is 0. So, the overall probability will be selection probability of this channel, which is 1 minus delta times 1 plus delta into 0. So, the capacity of a binary erasure channel is 1 minus delta bits per second. So, capacity is basically given by this. So, this example illustrates, so note that this binary erasure channel is not a strongly symmetric channel, but it is a symmetric channel because we are able to decompose this channel into two strongly symmetric channel, and since from the inputs we are able to reach these channel with same dispersion, so we can find out what is the selection probability of these channels, and subsequently we use this expression for capacity of a symmetric channel in terms of capacity of strongly symmetric channel and their selection probability to get the expression for capacity of binary erasure channel, which is 1 minus delta. So, if delta is 1, capacity is 0. If delta is 0, we can see that capacity will be 1. So, with this we conclude our lecture on channel capacity. In the next lecture, we will talk about Shannon's noisy channel coding theorem. We will prove Shannon's noisy channel coding theorem, and then we will prove the converse of noisy channel coding theorem. Thank you.